So we're here in our case 2. Suppose m is in the range of f. So then m comes from something, k. So now, So now I can say existential instantiation, get k in the domain, so that's n, such that f of k is m. So here I'm using this idea that the range is the collection of f of things, so it's the outputs of f. To be more precise, I'm using theorem 52. If something is in the range, then it's f of something that was in the domain. So that's where k is coming from. Next, I want a, so I've got my k. Next, I want to construct my swapping function g that swaps k with scare quotes n minus 1. Okay, so there's nothing actually scary about n minus 1. We just have to define minus, right? But we don't need to, so I'm not putting in the work of doing it. Instead, what is n minus 1 really? It's the predecessor of n, right? It's something whose next, or whose plus 1, is n. So it's something that when you plus 1, you get n. And we do have a theorem about getting predecessors. So to be able to talk about n minus 1, I'm going to refer back to that theorem. So here it is. The theorem says if I have a natural number that's not 0, then it's the next of something. So then it has a predecessor. So I need to verify that my n here is not 0. Yeah, I just need to verify that it's not 0. Well, it has k in it, right? So it's not the empty set, so it's not 0. So in other words, k is a natural number that's less than n. 0 doesn't have anything less than it. So since k is an n is not 0. Thus, by theorem 98, there is some what to call it? What to call this thing? I'm not going to call it n minus 1 because then that looks like I'm defining minus. I think in the written notes I call it s, but I don't know why I chose that notation. That seems confusing to me. How about I call it n prime, since it's like related to n. So instead of n minus 1, I'm going to call it n prime. So then there's some n prime a natural number n prime such that n is the next of n prime. In other words, n prime plus 1. So that's what I get from theorem 98. Okay, so now I've described this. This is n prime. Let me just call it n prime here. And the function g that I want is going to be something that swaps k and n prime. So one thing I could do, so what do I want g to be actually? I want g to be basically the identity function on n, right? Except instead of sending k to k, it sends k to n prime, and instead of sending n prime to n prime, it sends n prime to k. So this is what I'd have to do. Let g be the identity function on n, except remove the part of it where it sends k to k, and the part of it where it sends n prime to n prime. And then throw in a couple of pairs, namely the one that says k goes to n prime, and the one that says n prime goes to k. So this is how you would define g to have it operate like this picture is suggesting. Then you would have to prove that g is a function from n to n and is bijective. Okay, this will be a lot of work, actually. And it's more the tedious kind of work. Although, it's a good exercise if you haven't sufficiently practiced with the concept of bijection and mappings and things like that. But once you're used to those ideas, this is pretty tedious. So what I have done, sometimes I do this when something is very boring to actually write out, is write it as a theorem, check on my own on some scratch paper, verify that it does really work, and then I make it an exercise so that I don't have to write it. Okay, so not all the things in the notes that are exercises are really worth doing carefully. This is one of the sort of boring ones. I mean, I guess it's worth doing carefully for the sake of correctness, but it's not for the sake of insight. All right, so this is a theorem that will provide us with element swapping bijections. So if you've got a set and two elements p and q, then you can take the identity on the set and then delete the parts where p goes to p and q goes to q and throw in swapping rule. Then the result here will be a bijection from the set to itself that swaps things as it's supposed to. So that gets us out of having to do a lot of work. It's not really getting us out of it. I mean, the work is here. We're just pushing it away from our work in proving theorem 122. So here then, I'm not actually going to define G. I'm going to use the fact that according to theorem 121, there exists a G that does what I want, that swaps things. So by theorem 121, which we should feel guilty about using because we haven't proven, there exists there is a function. Usually I say we can get, but often people say just there is, and then they get it in the same line. We can get a function g mapping n to itself such that g is bijective and it swaps things. It swaps the things that we want. And g, so notice that n prime is an element of n. That's because n prime is less than n, right? N prime is less than its own next. So n prime is an element of n, and k is an element of n. So those are the two things we'll be swapping. So g n prime equals k, and g k equals n prime. So actually, since in this proof I'm only getting g from theorem 121 and not paying attention to how theorem 121 was proven, I actually don't really know in this proof what happens to all these other guys. All I know is that there's a swap here. And these other guys might get fixed, they might get moved around. But I know there's a swap here, and I know g is bijective. So anyway, not important, just interesting. By arranging things this way, we don't really know what g does to all this other stuff, and we don't actually care. So what's next? I'm trying to put myself in a situation where I can use the induction hypothesis. So let's pay attention to G followed by F. So F composed with G. So then F composed with G maps N to, let's see, so F goes N to M plus 1. G goes N to N. So F composed with G goes N to N to M plus 1. So F composed with G is this kind of map, N to N plus 1. That's just expressing what we see in the picture here, that it starts from this box and ends you up in this box. And by the way, for that, you're probably aware that we're using our essence of composition result that tells us what kind of mapping we get when we compose two mappings. But also, we're not just composing any two mappings, we're composing an injection with a bijection. And bijections are injective, so we're composing two injections. And here, if you have two injections and you compose them, the result is also injective. So then F composed with G. So we didn't really need that G is a bijection, actually. We just need that G is an injection, right? Then F composed with G and F composed with G is injective. Thanks to Theorem 78, Part 1. All right, so far we've got our composition from beginning to end here, and we know that it's injective. Now, let's verify this part of the picture that I keep pointing out, that n prime goes to m. So, we have, let's apply F composed with G to n prime. That's F of G of n prime, right? But G of n prime is k, so that's F of k. And k was chosen, it was its purpose in life, k's purpose in life. It was gotten for the purpose of having F of it be m, right? That is the entire point of k. So here we are. F composed with G sends n prime to m. Now I want to take my composite function and then delete this edge from it. Then I think what I'm left with should be an injection from a smaller natural number here to just this part, which is m. And then I think I can apply my induction hypothesis. So next goal is delete this edge, the n prime m pair, from this composite that I've got. So I want to know that, I want to know that if I take this and I delete that pair, n prime m, which is an element of this set since I'm seeing that n prime gets mapped to m, I want to know that that maps a smaller set. What smaller set? Just this stuff, excluding the n prime, that would actually be the number n prime itself, right? So it maps n prime to, and then a smaller set, this one, m. So that's what I want, and I want it to be injective. So there's something to prove there, right? There's definitely something to prove here. That this mapping statement, this is a function, this is its domain, the range is contained in there, and it's injective. But it seems like that's pretty clear intuitively, at least, or from the picture, just from knowing that n prime gets sent to m, and then we're deleting that pair. And that it's starting out as an injection. So it seems like it ends up injective. So here's another point where I'm going to push a whole bunch of work onto some other thing that you could then do if you want to or not. Exercise 73, way back in our section on functions. I don't remember if I assigned this or maybe I made it a presentable problem, maybe someone presented it. But anyway, it gives us exactly what we want. If you have a function, something in the domain, the function is injective, and you take the function, then you delete from it this input-output pair, then you get a function from there to there, and it's also injective. I guess it doesn't say that, but I wish it also said it's injective. Let's pretend this says and G is injective. Okay, actually, there's a very nearby exercise. You don't have to pretend anything. There's a very nearby exercise that says if you have an injective function and then you take a subset, also known as a restriction of the function, then that will be injective. So a subset of an injective is injective. Okay, then going back to this exercise, G here would be F delete something, right? So that will be a subset of F. So if F started injective, then G would be injective. All right, so pushing all the work to this exercise that we haven't done in the lecture in any way, what do we have over here? So by exercise 73, and also that other one I was using, 76, I have that if I take this and I delete n prime and then this applied to n prime, right? If I delete the input-output pair, which I've computed that's m, right? This composite, where is it? This composite applied to n prime is m, so I can just put m there. That this maps n delete n prime to m plus 1, right? It's the original mapping, but this one delete this, and then this one delete this. So m plus 1 delete m. And there's yet another exercise which we've already used in this theorem, but we're using it again, which says that if you take a natural number, and you delete its predecessor, let me phrase it this way: you take a natural number like next m, and you delete its predecessor m from it, then you get m. So this is just that statement that if I take this box of stuff, which is 0 through m, this is called m plus 1, and then I remove m so that I'm left with just the part that is circled in red here, then that's m. So according to that result, this is n prime and this is m, since n prime is the predecessor of n and m is the predecessor of m plus 1. So that was exercise 122. 122 is also being used, and that lets me write this as n prime and this as n. Whew, finally. Oh, and it's injective. That was like exercise 76 or whatever. Okay, so finally, I can use the induction hypothesis. Finally. I can use this. I'd have now proven that not n injects into m, but n prime, right? So thus we have an injection n prime to m. So now we can throw away these functions and stuff that we were composing. Don't care anymore. Our goal is to show n prime can be injected into m, and we have shown that. And now you can see why this for all is useful, right? We didn't have to work with the same n that we started with here to apply the induction hypothesis. So we've got n prime injects into m, and so therefore by the induction hypothesis, n prime is less than or equal to m. By the induction hypothesis, n prime is less than or equal to m. All right, now remember that n prime is something which plus 1 gives you n. So, and our goal is to get n is less than or equal to n plus 1. So now I can just plus 1 both sides of this inequality. You can justify this idea by theorem 99. I guess this plus also consider the case where you have a less than or equal to. Or we could go down to here and use this, except you would also have to consider the equality, the possibility of equality, but there's no problem there. So you should be able to get a less than or equal to version of this in like one step. So I can now +1 both sides. So this is n, right? N prime plus 1 is n. And that's what we needed. We're done. Finally. We have now proven, we finished the induction step and we've proven this. So now we can definitively answer the original question, does n have m elements? Here where n and m are natural numbers. The answer is only if n is m. Only if n is m. If and only if n is m. And what I was stating there was theorem 123, which we already saw last time how that follows from theorem 122. And there are a couple of immediate, very nice things you get, one of which I'm making a homework problem for you. I think it was this one maybe, or this one. I forget. But if you have any set having n elements and another set having m elements, and you manage to find an injection from one to the other, then it follows that n is less than or equal to m. So that will be not so hard to prove, given all the hard work we did proving theorem 122. So hopefully you can imagine why knowing something like this would be an important thing to know if you want to study finite sets. And another, this is basically just a way of rephrasing the same thing, is that if you have a set with n elements and a set with m elements, and m is less than n, then you cannot have an injection in this direction. So it's not possible to inject a larger set into a smaller set when you're talking about finite sets. It's not, so here when I say larger and smaller, I mean in terms of the number of elements they have and comparing those natural numbers using our ordering on the natural numbers. It's impossible to map something with bigger natural number of elements to something with less injectively. So that's called the pigeonhole principle. If you have n pigeons and you're trying to map them into m holes, and you have more pigeons than you have holes, then the mapping will not be injective. There will be at least one hole that has more than one pigeon in it.